And hopefully some people will watch some of this, and I'm going to just give a brief review. Today's my 12th day for this module, and Dr. Belmar will be doing all the days next week, and one day into the next week after that. I think he might have to miss one day, so he's going to give you a day off. He'll let you know that schedule. I think it's on Stellar. The schedule's on Stellar. And we'll start the presentations on the 19th, okay? Everybody is supposed to watch 20 student presentations. Now, they're going to be videotaped. Doing your own counts as one, okay? So you have to watch another 19. They're going to be about 33 of them or something like that. You don't have to watch them all. A number of students have said they like the presentations as well as the lectures. And frankly, the students do a good job on these presentations because it's something of interest to you, okay? And people do a better job and know more about things that are of interest to them in general. You also are supposed to, for different modules, kind of come up with a half to 1 page outline, although unfortunately in the past the students have been doing 2 and 3 page outlines of each module, okay? I think I mentioned it one time in the introduction thing that there's usually only 1 or 2 themes a professor can get across in an hour, okay? And that's all we want to know is what was the theme that you selected. So if I gave 12 lectures, there's only 18 to 24 themes, okay, in my whole 12 lectures. Can you actually distill it down to that kind of basic stuff? And I had one student once complain he thought that was busy work, and I don't think it really is busy work. I guess I disagree. I think it's good for you to say, okay, well, what's the basic idea here? Particularly when I ramble with stories that are semi-relevant and things like that. And then, what else do you have to do? Dr. Belmar will remind you. He's better on these things than I am. But anyway. So you have to watch 20 student presentations. You have to summarize all 3 modules. So there'll be kind of like 3 or 4 pages of summaries, and you have to turn those in. And then attend the classes, and that's it. Okay? Okay, so today I was going to talk about composites and do another case study. Yesterday was sort of, yeah.
Just a quick question on the logistics for the summaries. Do you want us to break it up by lecture?
Yeah, you can do it any way you want. Because it's for you, not me.
Okay.
I want to see that you did it,
Sure.
but I'm not going to study it. Okay? I mean, it's really for your benefit. And that's why I don't think it's busy work. Okay? But we do kind of look at them to see kind of what did the students really get out of these modules. Okay? In fact, one of my, he's a postdoc now, but he'd been one of my doctoral students. He basically says, well, Joel Clark teaches materials economics one way, and someone else teaches it another way. And what I've been teaching here, in terms of structural materials economics, is really sort of at a manager level, a senior manager level. I mean, a senior manager should know that it costs $10,000 a pound to get weight in orbit, okay? And so when they hear in the Wall Street Journal that that Elon Musk is going to start sending people to Mars, okay? Well, you can't even get them into orbit except for $10,000 a pound, and so someone weighs 200 pounds, we're talking $2 million just to get them into orbit, and we haven't even sent them to Mars yet. We could just leave them in orbit if they can't come up with the rest, okay? or drop them home, see how they survive. Anyway. Okay, any other questions on things? So the write-ups are for your benefit, so organize them any way you like, okay? Composites. Now, this is a typical type of overblown picture of composites. The only way you can tell it's composites is it looks like they got some sort of graphite fiber shell for the car, and you got this young girl essentially lifting up the car. What's wrong with this picture? The thing is wrong with the picture. What about the weight of that axle? Is she really that strong? I don't care how light the frame is, okay? There's a lot of weight in that axle and wheel and brake and everything, okay? And there might be an engine in there somewhere, okay? So I mean, this is sort of an overblown view, but you see these things all the time, and they're not quite as obvious as this one, okay? Now, the problem with composites, or a problem with composites, is what do you mean by composites? So we could be talking about concrete at 20 cents a pound, or we could be talking some fancy aerospace composite, and I've shown you this, and we're actually going to do a case on the X33 this morning. This is $12,000 a pound as fabricated in 15 years ago, okay? And we can talk about, if you want, about how you get to that price. But composites can have this 5 orders of magnitude. We talked about 5 orders of magnitude in different material properties. We can have 5 orders of magnitude in the price per pound for materials. And, you know, a dentist would call this a composite tooth. I actually have 2 in my mouth now as I get older. Titanium stud and a zirconium oxide crown, okay? They'll outlast the rest of my teeth, and they only cost about $5,000 per tooth, okay? Some people will get rid of their dentures, and, you know, if you want to have a $200,000 mouth, you can replace all your teeth with these, okay? It's embedded in the bone. This is a composite. It's actually a piece of artwork done by the CLT Wood Group, which is Composite Laminated Timber. And it's in London somewhere. It's called the Smile, if you look on the side. But basically, it's just made out of laminated wood product. Okay, that's nice. The problem with composites is it's one of the broadest terms in the field of engineering. Okay? It can be 20 cent a pound concrete, it can be super aerospace composites, it can be all kinds of things. Now, if we can take an aerospace example, and we can look at the last few aircraft that Boeing has built. And they started out with the 707, and then the 727, which no longer exists, and the 737, which still exists, but actually was completely redesigned around late 80s, early 90s. So the 737 of today is not the same as the 737 of 1975, but nonetheless. The Boeing 777, which was started in around 1990 or so, this is a $20 billion investment by one company. This is a bet your company project. In fact, does anybody know how Boeing got the 747? They lost the C-5A contract to Lockheed Martin, which wasn't Lockheed Martin. It was who were the people in Marietta, Georgia. It's now Lockheed Martin, but it had been a different aerospace company. I can't remember. Actually, one of my best friends' father worked there when I lived in Atlanta as a kid. But anyway, the 777 was a $20 billion bet your company project. They had an earlier bet your company project that was $4 or $5 billion, and that was the competition to build the super size air transport for the Air Force. And the C-5A Galaxy was the winning competition. And the Boeing, the C-130 is much smaller. Okay, the C-5A you can drive a couple of M60 tanks or M1 tanks on. Okay. And that's what they wanted, is the Army wanted an airlift to take tanks around the world. And the 747 was Boeing's entry into that competition. Back in the 60s, they would have 2 companies compete for the same thing, okay? And so Boeing had lost the competition, had invested billions of dollars of their own money, and they just said, well, why don't we make a commercial air transport? And everybody thought, oh, what would be the application of that? Whoever wants to have 400 people on a plane, okay? Well, I remember taking off out of Tokyo Narita once, and we circled over the airport, and I counted 47 747s on the ground, okay? Now, 47 $250 million airplanes. I mean, you're talking about $10 billion worth of planes right there at Narita, okay? Now, it's one of the largest hubs for 747s, but nonetheless. Anyway, the 737 in the late 80s, did this thing die? Anyway, I guess it did, okay. So I don't have a pointer until I get the batteries back. So the 737 was essentially an all-aluminum airplane. The 777, they said, was going to be all composite. That's when they put it on the drawing board and made the pitch to the board of directors. And it turns out, when they finally finished it, it was 12%, okay? And by the way, the guy who was in charge of the 777 program was Alan Lawley, an MIT grad. Actually, he was a Sloan Fellow, but close enough. And then he became chairman of Ford, okay? But chairman of the board of Ford. Or not chairman, president of Ford, then chairman, I think. Anyway, so they never hit their, all composite aircraft. So when they got to the 787, they decided it was going to be 100%, and it turns out, lo and behold, the actually, is there another? Can you look, Brian, and see if there's another pointer over there? The 787 ended up being 50% composite. And the darker blue, the royal blue you see there, is basically carbon fiber composite, okay? 50% by weight. That's because, just like my comment about polymers not being stiff enough, it turns out these composites would cost a small fortune to make the ribs and the keel beam and stuff. So it's still got aluminum and titanium. In fact, you see 20% aluminum, 15% titanium. So the internal structure is still primarily metals. But you can make the skin that goes on it lighter weight. And in order to compete and have low enough costs on the fuel, you've got to have a lightweight vehicle. So that's just an example. And if Boeing comes up and says they're going to build another major aircraft for $20 billion, a bet your company type of thing, then they may get to 80% or 75% composite. There's still going to be other things, okay? Now, whenever you hear about composites, because they are so broad, you ought to start asking a few questions. And here are the questions I came up with. Are we talking about structural or functional? Structural means mechanical properties. I'm actually taking you back to the very second slide on the first day of my lectures, okay? We have structural materials and we have functional materials. Functional materials are like optical materials or electronic materials, photonic materials, semiconductors, whatever, okay? Or could they be both? Smart materials, where you use some sort of functional sensor, which is a property of the material, but the material is also a structural material. People want to put fibers into helicopter wings that are strong enough to strengthen the wing and make a composite wing, but also have properties, whether it be piezoelectric or whatever, that can tell exactly what's happening to the helicopter wing in service and adjust things, okay? So that's a application of a smart material that's both functional and structural. So the advantage of composites is they're not limited to the same set of properties as conventional materials. You also need to know the target application and cost, and that's where I pointed out ships, autos, aircraft, aerospace. I mean, are we talking $20,000 a pound material, or are we talking $2 a pound over the life of the vehicle? And that, again, this is sort of a question a manager needs to ask. If I'm in the automotive business, don't tell me about $20,000 a pound aerospace composites. But people do all the time. And people will say, oh, Amory Lovins in the 1990s was this guy out of Colorado. He's an environmentalist, and he used to say, the automotive companies are idiots. We could build 100-mile-per-gallon vehicles today. Yeah, we could. Indianapolis 500 racers for $1 million a piece. You could have made a 100-mile-an-hour vehicle if you weren't going for performance and you were going for economy of fuel. 25 years ago, I could have built a 100-mile-per-gallon vehicle, but I couldn't have sold it for $25,000, okay? You're giving up something. So are you constrained by a specific industry? I mean, if you're going to an aluminum company, they want an aluminum composite. They're not interested in other materials. If you're into a functional, or not a functional, but an industry that doesn't care about the material, they don't necessarily have a material constraint. But some companies, by the nature of what business they're in, they will have a constraint. I mean, if you're Boise Cascade, you're in the wood business, okay? Trade-offs. Now, this is the one that people don't get most of the time. When you make a composite, you might be improving 1 or 2 or 3 properties, but you are probably destroying 4 or 5 or 6 other properties, okay? I can put silicon carbide into aluminum and make a stiffer, more wear-resistant, stronger material, but I can only cast it. I can't machine it because it's full of these silicon carbide particles. If I want to machine it, I got to use diamond tools, and it's very expensive, okay? I want to form it. I'm going to wear out my dies because it's full of all these abrasive particles, okay? I want to repair it. Well, there's no good way to do fusion welding of aluminum silicon carbide composites. In fact, back in the late 80s, when these aluminum silicon carbide composites became much less expensive to produce, a company came to me and said, oh, we want you to take our aluminum silicon carbide composites and electron beam weld them. I said, nope, not going to do it. I said, if you want to do that, you can go to Ohio State University. They got a welding engineering department. I'm sure they'll be happy to take your money. They said, why not? I said, because when you melt silicon carbide in the presence of aluminum, which you're doing in a fusion weld, you're going to form aluminum 4 carbide. And aluminum 4 carbide reacts with the humidity in the air and cause cracking. And they said, we want MIT to do it. So I said, fine, you can find someone else at MIT. I wouldn't take your money for this job. It's a stupid project. I didn't say that, but I tried to. I almost said that, I'm sure. Okay, it was 25 years ago. Well, guess what? They went to Ohio State, and one guy who didn't get admitted to MIT to do his work on welding got to do that work at Ohio State. And I know him now, and we talk about it every now and then, and he thought it was a lousy project when he finally learned about it. Okay? And he will admit it was a stupid project because you give up certain things. What's your time frame? Bringing a new material to market can take 20 years. There's lots of processes and things that have to be worked out. There's lots of ways people look at composites. They look at them as continuous fibers or short fibers or particles. And the fibers can be in different plies, so you can be, they call it 0, 45, and 90 degree plies. And so when you see something like that carbon fiber vehicle that the young girl was lifting up so her sister could get the soccer ball or whatever, that's basically multiply.
With the aircraft that has the 50% composites,
Yeah.
I know at least in Australia for Qantas Airlines, they had to ground their whole fleet a few years ago, right after I flew back, because they had a couple delamination issues.
Oh yeah, wow.
Then they didn't really know how to fix it.
Right, it's not repairable. One of the problems with composites is they're not really very repairable. That's one of the things you give up. They're not very joinable. This X-33 space plane, this is 0, 45, 90 ply of carbon fiber laminates. You can also make, and we passed around copies, things of these types of things. This is one right here. This is the honeycomb, okay? And you can do a 90 degree to the vertical, and you can do all kinds of other structures. Weren't you supposed to be working on that for your master's thesis? Yeah. Okay. Anyway, but lots of people are doing that type of stuff now. We can have laminar composites. So if we want to think of the smile, the wood thing that I showed you in the beginning, they've taken plywood to a new level, okay? And all these engineered wood products are basically composites of polymer and wood. They're just adhesive and wood. And the wood is the cheaper material, and so if you look at those things, I brought them in before, but the adhesive in there is very, very thin because it's very, very expensive, okay? Cheapest adhesives, polymer adhesives, are going to be about $2 a pound. I mean, you can get them for 10 and 20 cents a pound, things like cornstarch, okay? I mean, you get some really cheap adhesives, but they also get attacked by moisture. If you want to start getting adhesives that won't be attacked by moisture, you'll find in my welding lectures that when I talk about adhesives, typically you got to get up to $4 to $10 a pound to get moisture resistant adhesives. And I'm talking about things that are going to be moisture resistant for 10 or 20 years. You can get plenty of things that are good for 3 or 4 years, but not everybody likes their whole thing to delaminate. Just like, as Brian said, the Qantas airline, okay, reinforced composites. So they learn about the problem of adhesion. You can have honeycomb sandwich, and this honeycomb sandwich allows me to get into the X-33 space plane in a little more detail. Unless people have any particular questions. We don't have, this is a case study, so
I think most of the time when you think about composites, you think about carbon fiber composites. Like what other kinds? You mentioned that composite is like a very broad field, like includes like wood and carbon fiber. Like what other examples are there?
So, well, concrete is a composite, okay? It's stone and Portland cement. Reinforced concrete is steel, stone, and Portland cement, okay? That's at the low end. I mean, if I go to these things, this is Nomex, which is a high-strength polymer fiber that's been made into a paper type of material with a resin in it. You said, well, mostly you think about graphite. Why carbon fiber composites? Why do you think of that? Are you in the automotive business?
I did an internship in an aerospace company.
Okay, so, and you'll see that Boeing has a lot of carbon fiber composites. We had a similar type of fiber composite for 60 years, 80 years before that. It was called fiberglass. Before we had carbon fibers, we had glass fibers, which I told you yesterday, if you take those glass fibers as soon as they're formed, they'll be stronger than steel. They'll be just as strong as the carbon fiber. But carbon fiber is lighter, and the costs have come down dramatically. The way BMW was able to build the i3 is they basically took carbon fiber, which is so expensive that it could only be used in the aerospace industry, at $200 a pound per pound saved, right? And they started with a premium vehicle. That BMW i3 is like a $50,000 mini car, right? And they put the construction of that fiber in the Pacific Northwest, where they have lots of hydroelectric power, because to form carbon fibers, you got to put things in the furnace. You got to put the polymer in the furnace at 2,000 degrees centigrade. That's a tremendous energy cost, electrical energy cost. So they had to move their manufacturing to where the energy was cheapest in order to get it down. And then there's all kinds of other things they did. It's a very interesting systems thing. It's actually one of the students' presentations in this class, one of the LGO students who happened to have been interested in it for other reasons. And he had a couple of presentations, but he did a wonderful presentation on how the BMW i3 took about 5 or 6 different ways to drive the cost down, but it's still a $50,000 small car that you could buy another small car made out of steel for $15,000, okay? So you're paying 3 times as much for carbon fiber. Carbon fiber is still generally too expensive. And I talked to one of my doctoral students who's a partner at McKinsey now. He bought an i7, which is also carbon fiber BMW. And Chris did his thesis on polymers, and he knows all about composites and the resins and stuff. And I told him that I was putting in, I'm going to have 10 kilowatts of photovoltaics in my house when they finish it in the next month. And so I might buy an electric vehicle. I could become net energy zero with 10 kilowatts of power on my roof and a Tesla battery in the basement, right? And tell Belmont Light to go pound sand, right? Because the state of Massachusetts has told them they have to buy back my power, okay? But nonetheless, Chris tells me, he said the quality of the resin transfer molding of the BMW i7, which will go 0 to 60 in under 3 seconds, okay? Fantastic performance. That's what Chris wanted. He says it stinks. He said you couldn't build an airplane out of something that crappy, okay? So it's junk, okay? But it's good enough for the shell of an automobile, because all it has to do is deflect the wind, right? It's not really structural, but it's structural on Boeing aircraft, and the fibers have to be in the right place in the right orientation. So lots of people can make a cheap thing, and they learn to make it cheap, and they get better and better until they finally end up with something that's really structural. In the meantime, there are some people who decide they want to build a composite structure, and this X-33 spaceplane, the whole thing is a composite, but on different levels. But anyway, did that answer your question?
Yeah.
Okay. Other questions? I mean, we don't have to go into the spaceplane. I'll kill the rest of the hour on the story of the spaceplane.
One of the first locations it looked on that they turned to composites was the nacelle.
On the aircraft?
The 12% slide.
Yep.
Is there, I mean,
Here's the nacelle right here, the green, okay? And you'll see if you go to the nacelle is also, in this case, it's titanium. Oh no, maybe carbon sandwich. Probably carbon sandwich rather than titanium. I mean, I'm colorblind, but anyway. Okay.
they use that location just because it's not, I mean, it's just an encasement? Or?
Well, it's not just an encasement, but yes, okay. It turns out the cost of the engine is about $5 or $10 million. The cost of the nacelle is also about $5 or $10 million. So on like 787, it's probably $10 million an engine, and it's about $10 million per nacelle. And the nacelle, you're right, it's just sort of a shell on the outside, but it's got the major structural components that have to take all those 100,000 pounds of thrust out of that engine and transfer it into the wing, so there's some interesting structural parts. I've seen some failures of some nacelles, and you got pieces of high-strength steel that are 3 inches square, and you see some of the accidents, and this stuff is twisted in two and stuff. Some big forces on a nacelle, okay? And a lot of technology, a lot more technology than I realized went into a nacelle until I started looking at some of the failures. Okay, you learn a lot from the failures. Anyway, other questions? But you're right, Brian. Some of the earliest composites was the outside of the nacelle. You'll see that, in the 12% on the 777. They were putting it in the nacelle because at that point it's just a windbreak. Okay, and that's what it was on the BMW i3. It's just sort of a windbreak. Okay. Other questions on that? So there's lots of different levels of composite. Here is a composite structure made of subcomposite structures that was a $1.3 billion program that failed because they were a little too aggressive in trying to push new technology, including composite technology. So the X-33 spaceplane, I mentioned it before, it had liquid oxygen in an aluminum tank originally. They were going to try to get it to a composite tank, but there's real problems with holding liquid oxygen in a composite. It's problems with holding it in aluminum too, but anyway. The two hydrogen tanks were basically ended up being this is a piece from one of those hydrogen tanks from the X-33. And they had to build 2 of them. They were in 4 lobes apiece. They would lay up these things in 4 lobes, or individual lobes, and put them in the autoclave. And then they would essentially join these together with a bunch of adhesives. There were Inconel, these struts and stuff in here, these little round tubes and stuff. Those were things of Inconel and titanium, okay? But these multi-lobe hydrogen tanks, this was the final decision to kill the program. It had 2 Aerospike engines that had been developed by NASA Stennis Center in Mississippi. And so there were metal parts, but the whole structure included, the main part of the strength of the structure included these 3 tanks. And the stuff on the outside was just the skin to give it aerodynamics. But not only that skin that gave it aerodynamics, these little wings, this thing was supposed to be single-staged orbit, which meant you carry all your fuel with you, get up to space, and then you come back down and you land it. Do you think these little wings were going to be sufficient to take this thing that weighed 140 tons to land it? Of course not. It turns out the whole structure was the wing. The shape of that triangle turns out to be the wing. It gave lift. Now, it didn't have to give fantastic lift because it would take off vertically like a rocket, and it had to have just enough lift to be able to land in a way other than a rock. Okay? Had to glide. Okay, it's a glider. Okay? So anyway, they were, if you look this up, the Lockheed, I guess it was Lockheed before Lockheed Martin that did the C-5A and beat Boeing out for the aircraft transport back in the 60s. The X-33 Lockheed Martin was supposed to replace the space shuttle. It was supposed to be single-stage to orbit. The problem with $10,000 or $20,000 a pound in orbit is that you have to throw away your vehicle on every trip, and that's kind of expensive. And that's one of the things that SpaceX has done. SpaceX has a returnable vehicle, in theory, as long as it doesn't blow up on the pad, okay? Which they do. We can talk about those statistics. But in any case, if you can bring back your structure and reuse it, and that's what the space shuttle was supposed to do. And the idea was going to take the space shuttle, if you go back and look at the claims and the justification, they were going to take $10,000 a pound in orbit and drop it to $1,000 a pound. Now, it turns out they had enough problems that they actually raised the price to about $40,000 a pound. Okay, the space shuttle was never cost effective. But it was our main way of getting things in space for 30 years. And we had a fleet of 5 of them, and when we lost one of them, we built another, so we had a fleet of 5. But finally, it was just too expensive to maintain, and they decided they could go back to the old disposable rockets. Now, one of the ways they justified it is NASA basically said the space shuttle, they did big studies. I mean, in fact, a guy, Ed Roberts, over here at the Sloan School, was one of the guys who helped NASA learn how to manage huge projects like the Apollo project, putting a man on the moon. So there's some people at MIT in the management school that basically said, how do you manage something as huge as putting someone on the moon? This is a very complex project. And so they developed techniques to look at reliability and things. And they had calculations that they told Congress that the space shuttle had one chance of a disaster on takeoff out of 10,000 operations, 10,000 takeoffs. Now, does anybody know what the actual failure rate was? Was it 1 in 10,000? Well, when the Space Shuttle Challenger went up and failed, it happened to be the 25th shuttle flight. And one of the guys who was on the commission to evaluate what happened in the Space Shuttle Challenger was a guy named Richard Feynman, who won the Nobel Prize for quantum chromodynamics at Caltech. But he was an MIT undergraduate in physics. But Feynman pointed out to the commission that since Werner von Braun had come from Germany after World War II, and all the rocket flights out of Huntsville and Cape Canaveral and Edwards Air Force Base, 4% had failed on liftoff, okay? But NASA supposedly, because of these calculations of reliability, claimed that the space shuttle was going to be 0.01, not 4% reliable, but 0.01% reliable. And Feynman pointed out it just happened to be the 25th shuttle flight, so that's your 4%. Well, that's obviously, in those statistics, it could have been any time between 0 and 50, right, or 1 and 50. But it just happened to be at 4%, okay? But it was a good way of, because the lay people don't understand statistics. And Feynman made the point is they fail 3% of the 4% of the time. So SpaceX had been touting that their aircraft were going to be single stage to orbit, and they have been, and that they would be much more reliable. They would be, I can't remember, I was reading this stuff a week ago. It was something like 1 out of 100, okay? Or it was better than that. Maybe it was like 1 out of 300. 99.7% reliable or something. Well, it turns out the SpaceX shot that failed was the 30th. Okay? So we haven't really improved too much from the 4%. Okay? So people can wish that things would be more reliable, but that doesn't make them more reliable. And that's sort of another management principle. Well, this one had so many new pieces of technology in it that it failed. And the reason this particular one failed is sort of an interesting thing in composites. The original, well, first of all, after the Gulf War, the first Gulf War, we took 6 months to mobilize in Saudi Arabia to invade Iraq and take back Kuwait. Now, not every enemy is going to watch you mobilize for 6 months and wait for you to attack, okay? And the first Gulf War lasted either 3 days or 7 days or whatever. It's sort of like the Israelis and the Egyptians. It was all over in just a few days once they decided to attack. But they needed to mobilize, and they had all kinds of problems. Like all the helicopters had not been designed to operate in a sandy desert environment, okay? And it turns out when they got over there and they were doing some of their initial stuff, they found the helicopters were losing their engines in 24 hours because you start putting a brace of sand through an engine and it sandblasts itself apart, okay? So they had to develop better engine-air particle separators. Anybody know what an engine-air particle separator is? It's called an EAPS, E-A-P-S, right? Well, you have one yourself. It's called your nose, okay? And if you're in a dusty environment, you've been out working in the garden and it's all dusty, or you're in a coal mine and it's all dusty, and you breathe air and it has to go up and over and around. And it turns out the particles that can get into the worst parts of the lung are between 1 and 10 microns. And particles larger than that, or of that size and larger than that, will not be able to turn the corner. They have enough momentum that when the air has to go 180 degrees to turn the corner, and several 90 and 80 degree turns, their momentum just keeps them going straight. And they hit the mucus on the walls of your nose, and that's when you blow your nose, you see all the dust that the mucus is designed to catch, okay? You have an engine-air particle separator, 2 of them right here, okay?
Or if you've been welding.
Yes. Yes, I mean, whether it's welding fumes or whatever. And the reason asbestos gets down in the lungs is because it has a aspect ratio. I have chalk, you always hide the chalk. So let's say this 5 micron particle of dust is heavy enough, it will hit the wall when it tries to turn the corner. A asbestos fiber can be much longer. It could be 20, 25 microns long and only 1 micron in diameter. And guess what? It will go with the flow. It won't take that direction because it has a different drag coefficient. Your nose was not designed to breathe asbestos. And so the asbestos fibers get down in the lungs, and it's just aerodynamics, folks. Anyway, so the X-33 space plane, they decided, it was after the Gulf War, the first Gulf War, and they had learned about the importance of rapid prototyping. That was the big buzzword in Washington and on Capitol Hill. And NASA sold this to Congress as a $1.3 billion program that was going to be able to rapidly prototype from letting the contract to first flight, 33 months. Had to design it, build it, fly it in 33 months. It's going to be a demonstration of how quickly you could prototype a very complex thing. It was going to replace the space shuttle. It was half the size of the Venture Star, which was the design that was going to be large enough to replace the space shuttle. The cargo bay here was 5 feet by 10 feet, whereas on the Venture Star, it was going to be as large as the space shuttle. You had to get those lasers in space for the Air Force, right? So, in any case, that was what they sold. And what they had proposed, and the people who got it was the Lockheed Martin Skunk Works at Edwards Air Force Base in Palmdale, California. They proposed using three-dimensional woven carbon fiber composites. Well, the problem with that, this is just a ring-stiffened cylinder like a submarine, okay? You got a cylinder and you got rings on the inside and beams and to stiffen it. And they were going to make those beams out of carbon fiber composites that were a three-dimensional weave, so you'd have your two-dimensional weave, you'd lay them up, and then you'd have people with needles and thread, literally, hand sewing carbon fibers across these plies to get the three-dimensional structure. That's the only way people knew how to do it. So they went out to price it, and they found this was going to consume the whole budget to build these things. They said, well, that won't work. And they only had about a month or two left to design the hydrogen tank. And they said, wow, we can buy off the shelf this Nobex honeycomb, and we can buy adhesives, and we can buy carbon fibers that we can laminate. We already know how to make carbon fiber composites from the aerospace industry. And we could build these hydrogen tanks. And up there at Morton Thiokol in Logan, Utah, we have autoclaves that are large enough that could build lobes, autoclave a whole lobe, 1/4 lobe of this tank, or 1/4 of the tank. And so they decided to build 10 of these lobes, and they put them in the autoclave, heated them up, and 2 of them were junk, and a couple of the others were sort of had some delaminations, and it wasn't a good day. So they sharpened their pencil, and they measured the strength of these delaminated areas. They could measure them with ultrasonics and stuff. And they decided instead of a safety factor of 2, they had a safety factor of 1.05. Okay, anybody know about strength safety factors, typical values? This building you're in, well, is by law has a safety factor of 5/3 mechanical strength, 1.67. The bridges you drive over by law have a safety factor of 2 because of vibration and things like that. You climb a ladder. Anyone ever been up on a ladder? That's got a safety factor of 4, okay? Because OSHA requires a factor of 4 for scaffolding. The more hazardous something is, the bigger the safety factor. So they had designed this thing. They can't go too big because it's heavy, okay, to make things safer. And they designed it for 2.0, but because of the delamination during autoclaving, they found they only had 1.05, but this is a $1 billion project. 1.05 is greater than 1, and so it should work. So they took one of these tanks, and they put it in test in Huntsville, Alabama, and, we'll talk about the test in a second. But basically, this was the laminate that instead of the three-dimensional woven composite, which was way too expensive, they were just going to take the carbon fiber 0.45 and 90-degree ply, and they're going to have this sheet of epoxy, and then they're going to have the honeycomb, which you can buy off the shelf, and you just make a sandwich layer, and you're going to fabricate this. This doesn't have the other panel because it came off. And they went and they looked at a 3M data sheet for epoxy adhesive, and it said that if you take it out of the refrigerator, the epoxy is already made up in a big sheet by 3M, and they keep it in a refrigerator so the epoxy won't cure until you get it to the autoclave. And they looked at the PowerPoint slide that 3M had on their website, and it said, good for 10 days out of the refrigerator. Okay, they figured they could make those lobes, get them all built and into the autoclave within 10 days. And they did. They got them all in within 4 to 9 days. What they didn't stop to think about was the actual data. Now, this is not the actual data, but it's a typical curve for epoxy shelf life. This is actually for marine epoxy. But anyway, pot life in minutes. This is for minutes rather than days. And this is temperature in degrees Fahrenheit. But think of this as time out of the thing versus in days, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and strength of the epoxy that hasn't cured at room temperature. It's starting to cure at room temperature as soon as you take it out of the refrigerator, right? And they got to lay all this stuff up and form it, and then get it in the autoclave to join it and heat it up. And lo and behold, the curves look like that. Well, when 3M had their bullet point, they were talking about it had 10% of the remaining strength after 10 days. NASA had assumed that they meant it had 80 or 90% of its strength. Because it said right there on the bullet point that it had a shelf life of 10 days. But 3M defined the shelf life as good marketing people as 10% of the remaining strength, of the expected strength. And NASA assumed, well, that must mean it has most of its strength left, right? Well, they found out it didn't have the strength. It delaminated. And they said, okay, well, it still should be good. We calculate, after we do measurements on the other 2 cores that had failed, we calculate from statistics, we got a safety factor of 1.05. So they take it down to Huntsville, Alabama, because not everybody has a tank, a test facility with enough liquid hydrogen to fill up something this size, okay? This is scaffold in here, so this is about 20 feet tall and stuff. And you can see here's a lobe, here's a lobe. And they put it in test with the liquid hydrogen. Everything's just video. You don't have people around liquid hydrogen because if it goes boom, it's not a good day, okay? And everything passes as they cooled it down. They're warming it up. They're giving themselves high fives. And someone sees on the video about 2 to 5 minutes after it started warming up, they see this pop and a bunch of the frost comes off. And what had happened is they had done some tests of permeability of hydrogen through this graphite. Okay? Hydrogen diffuses through anything. But they had done some tests at Stennis in Mississippi, and they had some numbers, but the numbers were sort of fishy. Okay? When they went back to say, well, how'd you get that number? No one could tell them. Okay? Apparently someone pulled the number out of the air and gave them a number, and they did their calculations on that number. When they had the failure afterwards and they were trying to analyze the failure, no one could tell them where they got the number. And it turns out when they did the test for the first time, the numbers were off by about 3 orders of magnitude for permeability of hydrogen. Liquid hydrogen diffused through was inside these pores, and when that liquid hydrogen started to expand, it built up too much pressure and the thing blew apart. And they realized, cannot fly this thing. And that was the final Achilles heel that killed the program. So that's the X-33 space plane. A number of mistakes. One of them, it wasn't clear if someone bothered to, they couldn't reproduce the numbers when they were challenged. And the other one was when you start looking at bullet points on data sheets, sometimes you'd like to see the real data. Okay? It only cost $1 billion. What the heck? Okay. Okay.